Ma'am, shall we start now?
Yes.
Okay, ma'am. Okay, our distinguished guest, Professor Lilikuti Jacob, head of various departments, dear participants and colleagues. A very good morning to one and all. This is the very humble beginning of our FDP with the title Advanced Communication Systems, a Research Perspective. It is organized by Department of Electronics and Communication Engineering of this institute. So actually, we have 148 participants registered for this program, out of which 91 are from different states other than Kerala. So being an online course, participants across the country can attend the program from their office or residence. Similarly, the resource persons can also share their research experience comfortably from their office or residence. I consider this as one of the positive outcome of uh, current academic current pandemic situation. We are organizing this 5-day program to introduce and discuss various emerging topics in communication systems. We are actually fortunate to have very eminent resource persons from academia, industry, and research organizations. I know many of the participants are doing research or planning to start. Some of the well experienced researchers are also attending the FDP. So I hope each session will motivate or inspire you to pursue your research. In the 2-hour session, last 30 minutes are for discussions. So my humble request is to make use of this time to interact with the respective resource persons and make maximum benefit out of this course. With these words, let me come to my duty to welcome you all to this function. Today, we have the most eminent and one of the senior-most faculty members from Department of Electronics and Communication Engineering, NIT Calicut, to handle the first session. She has kindly consented to inaugurate the FDP also. On behalf of the College of Engineering, Karunagapalli, all of the participants and coordinators, I extend a warm welcome to you, ma'am. Next, I welcome all the participants from across the country to this course and to our college also. I welcome all our head of departments and my colleagues to this function. I would like to take this opportunity to appreciate the efforts put by my colleagues, Sri Shanuyan, Srimati Millie Roslyn Matthews, and Sri Venu VS for conducting this FDP right from the preparation of its proposal. So once again, I welcome all of you to this program. Thank you all.
May I now invite Rehana Raj to read the profile of Dr. Lilikuti Jacob.
It's my honor to introduce Dr. Lilikuti Madam to the distinguished participants of the FDP. Dr. Lilikuti Jacob received the PhD degree in Electrical Communication Engineering from the Indian Institute of Science, Bangalore in 1993. She was a postdoctoral fellow with the Korea Advanced Institute of Science and Technology from 1996 to 1997. She was a visiting faculty with the National University of Singapore from 1998 to 2003 and with the University of South Florida in 2012. She is currently a professor with the Department of Electronics and Communication Engineering, National Institute of Technology, Calicut. She has received more than 160 publications in international journals and conferences. She is an editor and a reviewer for several international journals and conferences. Her research interests are in protocol design, performance modeling, and analysis of communication networks. She is a life member of ISTE and a fellow of IEI and IETE and a senior member of IEEE.
Let me now invite Dr. Lilikuti Jacob for the inauguration of the function.
Thank you. Very good morning to all of you. Since Dr. Anil Kumar has asked me to inaugurate this function, let me just give a couple of words before I go to my session. First of all, I congratulate the Department of ECE, College of Engineering, Karunagapalli, particularly the principal, Dr. C.V. Anil Kumar, and the coordinators, Sri Shanu and Srimati Roslyn, for organizing this faculty development program on advanced communication systems and research perspective. As we all know, this FDP is being organized by AICTE Training and Learning Academy, ATL Academy, which has got the vision of empowering the faculty for achieving the goals of the higher education in terms of access, equity, and quality. See, for any higher education system, we know that one of the most important stakeholders are the faculty. So the faculty have the great responsibility of transforming the raw input to quality output. So in the output of the system is being measured in terms of the skills and knowledge of the students and their behavior and their attitude. So faculty have a great responsibility in transforming them to that level, who will be fit to the society and the corporate world and for the future of the nation. So faculty development programs have a great role in fact, training the faculty members, because the faculty members, when they start their profession, they have very primitive knowledge and skill. Over the years, they need to sharpen their or increase the level of understanding of their basics, the advanced topics, and their research aptitude. So faculty development programs are mainly meant to equip the teachers or train the teachers to do their task in the most effective and efficient way. That is transforming the students, the input students, with the necessary knowledge and skill to the quality output. So as I mentioned, the faculty development programs, FDPs, are mainly meant to help the teachers or train the teachers to improve their level of understanding. All these three, that is basics, because without the greater understanding of the basics, they cannot, a greater insight or different higher levels of understanding, they cannot have the understanding or comprehension of the advanced topics. And also they cannot have the better research aptitude. So to understand or comprehend the advanced topics and also to improve their research skill and the research aptitude, they should have a great insight into the basic subjects, basic topics. Okay? So that also they have to refresh every year. Year after year, they have to improve the level of understanding, because every basic subject has got different levels of understanding. Okay, so you should not be comfortable or happy with what all you know the basics, but you have to always try to improve the understanding to greater level. Okay, so in that sense, the today's my topic is a basic subject, that is a stochastic process. Okay, so with this, actually I am inaugurating this FDP program, and then I will now start with my topic because I have 2 hours is very little to give you the overview of the stochastic process. Of course, I am going to focus only on the very basics, so that you have a whatever level of understanding you have about the stochastic process, you can have even a little better understanding, I hope. Okay, a better insight into that topic, because without stochastic process, we can't do anything in communication. If you look at for example, let me take if you look at the wireless communication, see now we have 4G and then 5G, and in all these things you see that the wireless channel is an important aspect. And to understand the wireless channel, we should have a very good understanding of the stochastic process, because we know that the channel imperfections are all random in nature, and noise, everything, fading, small scale fading, large scale fading, and the noise, everything, they are all handled in terms of using the stochastic process only. Similarly, if you look at the internet, okay, in the internet again, if you look at the routers, there again the packet arrival process and the queuing and the resource allocation, everything we need to deal with the stochastic process. So how do we understand the papers on these research topic if you don't know the basics of the good understanding or insight of the stochastic process? Similarly, if you take wireless sensor networks, see in a wireless sensor network, you have large number of sensors, How do you model or characterize the locations of the sensors? You need a 2-dimensional or 3-dimensional stochastic process. And then you have to characterize the traffic arriving at the coordinator of the sensor network from the large number of sensors. How do you model that? Again, you need a random process to model the one-dimensional stochastic process to model the traffic that is arriving at the coordinator of the sensor networks. So I'm just emphasizing the importance of knowing such a basic subject. And also, we know that the teachers know you have very little knowledge about, when we start the profession, teaching profession, we have very little understanding of the probability, random variables, and random process. So through these kind of FDPs, you can definitely improve your understanding and if your insight on that topic. Moreover, now you can listen to some good massive open online courses, MOOC courses. Register for that, and then you have to do that sincerely. Then you can have even a better understanding. Because in 2 hours, I cannot do much to the particular topic. So without losing any more time, let me start sharing with my slides. Okay. Hope my screen is visible to you.
Yes, ma'am.
Okay. Okay. So let me just start with the definition of a stochastic process. Can stop my video. Should I stop my video?
Yes, please, ma'am.
One second. Okay. Visible, no? Hello?
Yes, ma'am. It's visible.
Okay. So underlying any random process, we have a random experiment. And the random experiment has got several outcomes. Corresponding to each outcome, we know a random variable means a random variable. We typically write it as like this, but typically we suppress this argument and just write x. But we know that this corresponds to, it's a random variable is a function of the outcome of the random experiment. Corresponding to each outcome, we have a typical real value. So corresponding to say one outcome xi1, we have one real value. Corresponding to another outcome, we have a different real value. So these small x1, x2, etc. are the real values that this particular random variable can take, and each real value corresponds to one outcome of the random experiment. Okay, so this is about random variable. What about random process or stochastic process? It has got two variables, two arguments. In addition to this outcome parameter, there is another parameter which we call the typically time parameter, but this parameter need not be necessarily time, okay, but we call it typically time parameter. So there are no two arguments, and so when this corresponds to the same argument for the random variable, that is outcome. So corresponding to each outcome, say xi1 of the random experiment, or we have a sample space where you have several sample points, we call it sample points, xi1, xi2, xi3, etc. These are called the outcomes of the random experiment, and this is called the collection of all these outcomes, which we call the sample space. Okay, so corresponding to each outcome, in the case of a random process, we have actually a function of the parameter t, that is xt xi1 for a given outcome. We actually have a deterministic function of the parameter t. Okay, so similarly, if you take another outcome, say xi2, you get another function of the parameter t. Okay, so these are called the realizations or sample function of the random process. So in the case of random variables, we skip the, we suppress the argument xi. Similar to that, in the case of random process, we typically suppress the outcome parameter xi, and we simply write it as xt, or sometimes we use it like this, or sometimes we write like this, and so on. So different notations are there, but when we know that it is a random process, we know that there are actually two arguments for that. Okay, so in that sense, when you we can define random process in two ways. One is that it's a collection of functions of t. So it's a deterministic function of time t, and we have a collection of such functions because for each xi we have a different deterministic function or realization or sample function. So it's a collection of, so we can say that it is xt xi with the xi belonging to omega, that is the sample space. So this collection of functions of the parameter t, that is one definition of a random process. The other definition is, again, it's a collection of random variables. So indexed set of random variables, because for each t, if you fix t as equal to t1, then it is a random variable.
Teacher, your screen is not visible.
It's not visible now?
Presentation window.
No, I am using a white screen now.
Now
Is
it's
it
not visible, ma'am.
Yes?
It's not visible now.
Oh, okay, okay. It's not being shared. Oh, sharing was stopped.
Yes, ma'am.
Sorry.
I think someone else had tried to share their screen.
Yes, sir. Someone has started presenting. That's the problem, sir.
Oh. Is
And
it
now
now?
it is visible, madam.
Yeah?
Now it is visible.
Okay. Visible?
Yes.
Yes, ma'am.
Yes, madam.
Okay. So now I'm using my whiteboard. You can see that, no?
Yes, ma'am.
Yes, ma'am.
Okay. So what I was trying to say is the second definition of the random process is that it is a collection of random variables indexed with the parameter t. That is, for each value of t, we have, say for example, t is equal to t1. You get one random variable. Okay. So because for different outcome, the different xi value, it gives you different real values. Similarly, if you take another time parameter, say t2, again it is another random variable because for each xi value, that is the outcome of the sample space, we get a different random variable which takes different values depending upon the value of xi. So for each t, that is why we have now the second definition of the random process as the collection of random variables, an arbitrary set of random variables where each random variable is actually the corresponding to different values of the parameter t. Okay, so these are the two basic definitions of a stochastic process. Depending upon the context, we can use either this definition, that is an arbitrary collection of random variables, or indexed set of random variables where the indexing is on the parameter t. Or it can be considered as a collection of random functions, okay, which are called the sample functions or realizations of the random process. There actually, each one corresponds to different values of the outcome xi. So you have x t xi1 is 1, then x t xi2 is another sample function for, that is, it's a function of time t, but these are different deterministic functions corresponding to xi1 it is 1, and corresponding to psi 2, you have a different realization, and so on. So these are the two definitions, alternative definitions of a random process. So that is what our the first slide is on. So what we have shown in this figure 1 is that this is one realization. Okay, sorry. This is one realization, xi1. So you can see that it is a function of time t. Okay, so this is one realization, another realization, another realization, and so on. So this is a collection. This is the first definition of the stochastic process. Okay, so we have that is what is defined in this, the set of sample points or outcomes, and the time index t can be then coming to the, because we have two parameters, right? So we can have four possibilities. At t, the time parameter can be discrete or continuous. Similarly, the xi parameter can be discrete or continuous. Okay, so if t is discrete, then we call it discrete time random process, or if it is continuous, we say continuous time. Similarly, if xi, depending upon the value of xi is discrete or continuous, we have the random variables, because for each t we have a random variable. For different t we have different random variables. These random variables can take value either continuous or discrete. That is, the real values that the random variable take for each xi can be continuous or discrete, which we say as discrete or continuous state. So accordingly, we have four different types of random processes or stochastic process. One is, time state. The time can be discrete or continuous. State can be discrete or continuous. Accordingly, we have, say, discrete state, discrete time random process. Similarly, continuous time, discrete state random process, or discrete time, continuous state random process, or continuous time, continuous state random process. That is, the state refers to the random variables, because we have mentioned that this random variable, the random process is a collection of random variables. So if the random variables are continuous, we say continuous state. Random variables are discrete, we say discrete state. And the other parameter is the time parameter. Okay, t. So if it is a discrete, t takes only discrete values, then we say that discrete time random process. Also, we call the random sequence, because it's a collection of a sequence of random variables. So therefore, the discrete time random process can also be called a random sequence. Or the time parameter, if it is continuous instead of discrete, it's continuous time parameter, then we say continuous time random process. Okay, so in the reality, on the real physical scenario, we may come across any type of these four different random processes. For example, if you look at the Markov process, okay, Markov process is a random process, one type of random process. Okay, it can be continuous time or discrete time. Discrete time Markov process. Markov process means, I'm not going into the details of that because it will take a lot of time to discuss that. So Markov process is a type of continuous, a class of random process with a Markovian property. Okay, and if it is continuous time, then we call it as the discrete time Markov process are called the Markov chain. Markov chain means they are discrete time, a discrete state called the Markov chain. And in that again we have continuous time, CTMC, continuous time Markov chain and discrete time Markov chain. Okay, so that's what I said. Now there are depending upon the time parameter, whether it is discrete or continuous, and depending upon the state, that is a random variable which is continuous or discrete, we have all type of 4 different types of random processes. Of course, now you have come across different types of random processes, other type, classification like Poisson, Gaussian, Brownian motion, Okay, apart from this Markov process itself, we have DTMC, CTMC, then we have the semi-Markov process, then we have the Markov decision process, then hidden Markov process. So many varieties of the Markov process itself, that is random process with the Markovian property are there. Then we have several random processes. We will discuss only a couple of random processes only in this discussion because because of the constraint of the time. So keep the two definitions in mind as we proceed with this discussion. So for example, okay, I think what happened? Page 2 is missing. Okay, page 2. So here we have an example of a stochastic process. Okay, this is a sinusoidal process where actually a amplitude is constant, frequency is constant, only phi is random. So the phi is a random variable which can take any value, uniform random variable, uniform in any value between 0 and 2 pi. Okay, so depending upon the different values of phi, we get different realizations. For example, if phi is equal to 0, so different realizations look like this. For t, phi is equal to 0 because it is cos, we know that like this. If this is for phi is equal to 0, for phi is equal to pi, we have again. Similarly for different values of phi. So phi is a random variable. So depending upon the different values of phi, we get different realizations of this random process. These are called the different realizations. Okay. And for different values of t, okay, so for example t1, we know that this random process will be taking a specific real value, another t say t2. So it takes different values because t1 is a random variable which takes different values and different realizations. These are the different values that this random variable can take. Similarly, for t2, another random variable which takes different values, say these are the different values that, because this is t2. So at t2, what are the different possible realizations? Okay, so at t2, this is a random variable because it takes real values like this, and so on. Okay. So this is a typical example. Now, the next question is, how do you characterize a random process? For a random variable, we know that a random variable is characterized by its cumulative distribution function, CDF. Okay, so like this. Probability that the random variable is taking less than or equal to a real value small x, and we have to define it for the entire value, real values x. This is called the cumulative distribution function, or we can take the derivative of the cumulative distribution function, which is known as the probability density function. Okay, so this is the derivative of the cumulative distribution function with respect to x, and which is the PDF. This is CDF and this is PDF. So this is the case for a random variable, but in the case of random process, we have arbitrary collection of random variables. So how do we characterize a random process? Okay, so this kind of, we can, for each random variable, we can define either CDF or PDF, and this is called the first order probability density function or first order CDF. Okay, so now we have different, arbitrary collection of random variables means first order the first order density function or distribution function is not sufficient. We need to define second order, that is, take any two random variables from the random process and then define the join CDF and join PDF. And then we have to take three random variables, any three random variables, and then we have to define again join CDF or join PDF of the three. Like that, we have to define nth order CDF or PDF, and that is to be defined for every value of n equal to 1, that is first order, n equal to 2, second order, and for any finite value of n, we should have the description of the or character the model for the cumulative distribution joint CDF and or joint PDF. Then only the characterization of the random process will be complete. So that is what is defined in the slide. That is corresponding to t is equal to t1, we have one random variable, t is equal to t2, we have a different random variable. So we denote it by x1 and x2. Okay, so we have the joint cumulative distribution function defined in equation 3. Joint probability that the random variable x1 is less than or equal to small x1 and random variable x2 is less than or equal to small x2. This is the joint CDF. Similarly, this is a joint PDF. This is the derivative of the joint CDF with respect to both x1 and x2. Okay, so this is the second order PDF. So similarly, we have to define the nth order PDF. So you see that x1, x2, xn, t1, t2, tn. Corresponding to t1, we have one random variable. Corresponding to t2, we have a different random variable. So n random variables are defined. So this joint PDF means this one with n equal to instead of 2, we have n. So this represents the nth order density function of the process. So the complete specification of the stochastic process requires the knowledge of this one for all t, that is t1, t2, t3, and for all I, that is n, 1, 2, 3 up to n, and for all n. So we know that this is almost impossible task. Okay, so the complete characterization of a random process or complete specification of a process like this is almost an impossible task. So we need a lighter version or a easier way of which may not be complete, which will not be definitely complete, but partial specification is possible. Okay, so that is what we typically do in reality. Okay, so in that sense, we go to some of the parameters, statistical parameters to specify a random process. One important parameter is called the mean of a random process. Okay, the mean of a random process, which is defined as, we know the mean or expectation of a random variable. So if x is a random variable, we talk about the expectation or the mean as integral x fxx dx, right? That is this is the density function. So this is the expectation of a random variable x. These are the real values that x can take, and this is the density function, and then integrate it over all values of x, you get the expectation, right? So here we have the mean of a random process, because in random process we have arbitrary collection of random variables. So for each random variable, we denote it by xt, because it's a function of time t. For different values of t, we get different random variables. So therefore, we put it as like this. And now it's the definition is identical, the same. But only thing is that now this random variable is different for different values of t. Okay. So main function, we call it as a main function, because for different t, you get a different different values for the main. That is why we put it as a explicitly it is written as, instead of writing a, here we simply write mu, whereas that is the case of random variable. For the case of random process, we put it as a mu t, because it's a function of t. Okay, and now the next important parameter is the autocorrelation function. In the case of a random variable, we talk about variance. In the case of a random variable, we talk about x minus mu square. This is your variance of x, right? The second moment, x minus mu x. So similar to that, in the case of a random process, we have autocorrelation function, which is defined as expectation of xt1, xt2. This is actually expectation. If mu equal to 0, then we have e of x square, right? So similar to that, here we have the autocorrelation function where it is e of xt1, xt2. This conjugate, because now we consider random process xt as a complex random process, then we always use the conjugate. If it is a real random process, this is not there. Okay. So the autocorrelation function by definition is expectation of xt1, xt2. So therefore we have x1, x2, the joint density function of those two random variables, dx1, dx2 over into x1, x2. Okay, so this is the autocorrelation function. Now we can see that it is a function of two parameters t1 and t2 because we are taking two random variables at a time, xt1 and xt2. So therefore it is a function of two time parameters t1 and t2. And this autocorrelation function has several important properties. I just give only a couple of very important properties. One is that this is conjugate. So see this Rxx T1 T2 is equal to Rxx conjugate T2 T1. This means that the first parameter corresponds to first random variable. So it is expectation of xt2, xt1 conjugate. Okay, so this is expectation of xt1, xt2 conjugate. This is expectation of xt2, xt1 conjugate. So you can see that this is the relation between the two. The second point is that Rxx tt means t1 equal to t2 equal to t. Okay, so when t1 equal to t2 equal to t, then what you are getting is actually the average power of the process, E of xt square. That is the average power of the stochastic process, random process.
Madam,
Yes.
Madam, may I interrupt for a moment? There is a doubt in chat box. Shall I read it?
Okay, I think if it's in the full view mode, can we preserve all the questions at the end?
Okay, madam. Okay.
Okay. Because if I leave this mode, then again it will take to come back to this mode because of the use of the whiteboard. Or maybe at after first half, I can stop for a while and then answer the questions and then go for the next half. Okay.
Okay, madam.
Okay. Now the third property is that this function, that is the autocorrelation function, is a non-negative definite function. That is, for any set of real constants ai, we have this one is always greater than or equal to 0. That is called the positive non-negative definite the definite property, which you are familiar with. So this is a proof of that. I don't want to go to that. So these are the three very important properties of the autocorrelation function. Now coming to the third parameter, statistical parameter, this is called the autocovariance. Okay, autocovariance. This is similar to your variance. Variance of the random variable, we define it as variance of x is equal to e of x minus mu square. Okay, so similar to that, this is the covariance because we are talking about the random process. So it is, and here we know that for a variance of a random variable, we have e of x square minus ex square. That is e of x square minus mu square. Okay, this is the variance of x. Similar to that, this autocovariance is actually autocorrelation function minus mu x t1, mu x t2. Right, similar to this. Here it is autocorrelation. Instead of e of x square, we have autocorrelation function, and then instead of mu square, we have mu t1, mu t2. Okay, so this is the autocovariance. So the three important statistical parameters for a random process are main function, which is a function of parameter t, autocorrelation function, which is a function of parameters t1 and t2, and covariance function, which is also a function of the parameters t1 and t2. Here is an example. This example we will be using in a later context. So look at this. Here we define z, a variable, as integral of xt dt for t minus capital T to plus capital T. This is a random process. So when we take such expression means when we take one realization of the random process, we know that for a one realization, this is a function of time t, deterministic function of time t. So we can define this integral. Take another realization of the random process, we get another function, deterministic function of time t. So we get another value for this. So like that for each sample function of the random process, we have different deterministic functions, and corresponding to this integral we get different real values. So therefore we can say that z is a random variable which takes different values depending upon the different realizations. So this random variable, we can define the expectation of z square by substituting for z. We can get this expression, and then we have expectation actually outside this double integral, which because expectation is a linear operator, we can take that expectation inside the double integral, and then we have expectation of xt1 xt2, which is nothing but the autocorrelation function. So therefore we have rx xt1 t2. So thus e of z square is nothing but double integral autocorrelation function of the random process. Another example, we have earlier seen the function stochastic process, the xt, a cos omega 0 t plus phi, where phi is uniform random variable. Okay, so what is the main function of this random process? Mu xt, e of xt substitute this one, so you have e of this one, and again a is a constant, so you can take expectation inside and expectation of this. Okay, now you see that omega 0 is a constant, phi is a random variable. So this is actually a function of the random variable phi. Okay, cos omega 0 t plus phi is a function of the random variable phi. So therefore this is again a function of a random variable is again a random variable. So this is another random variable. Expectation of a function of a random variable, we obtain it as, this is a fundamental theorem of expectation, that is expectation of a function of a random variable you obtain as, again, using the density function of phi. That is, we corresponding to each value of this phi, we can have a real value g theta. Okay, g theta here, it's a function value with a specific theta value, phi value. And then we use the density function of the random variable phi itself. Okay, this is the density function, probability density function of the random variable phi. That is your uniform distribution. Uniform distribution means what? We have phi taking value uniformly in the interval 0 to 2 pi. So this is the probability density function f phi phi, right? For different values of phi, we have, this is 1 by 2 pi. So phi can take value anywhere between 0 and 2 pi, and the probability that it takes any value is 1 by 2 pi. So this is your density function. We use the same density function of the phi to get the expectation of the function of the random variable phi. So this is g theta f theta d theta. Okay, f phi, because usually the probability density function we denote by small f with the subscript, the random variable, argument, the real values that this phi can take. Okay, so now you have the expectation of this one, of this random variable. For that, to simplify that, what do you do? This is a cos A plus B. So cos A cos B minus sin A sin B. Cos A cos B means cos omega 0 t cos phi. Cos omega 0 t is a constant. So again, you can take constant out. So this is expectation of cos phi minus sin A sin B. Again, sin omega 0 t is a constant. So you apply the expectation only for the sin phi. Cos phi is a random variable and sin phi is a function of phi. So therefore sin phi is a random variable. So expectation is applicable only for that. So this is the expression. Now you can see E cos phi. We use this fundamental theorem of expectation to find the expectation of cos phi. So what is the expectation of cos phi? We take specific value of phi and the density function is what? 1 by 2 pi. So this 1 by 2 pi is the density function. Okay. Then we have the simplification is that now you have integral 0 to 2 pi cos phi d phi, because the density function takes value 1 by 2 pi, which we have taken out, and then we have integral 0 to 2 pi g theta is cos phi d phi. And if you take the integral of the cos phi over one full cycle, we know that it is 0. So therefore, we have e cos phi equal to 0. Similarly, e sin phi equal to 0. So therefore, this term is 0, this term is 0. So therefore, the main function is 0. Okay. So irrespective of the value of t, we find that it is a constant and it is equal to 0. Fine. The second parameter is the autocorrelation function. Again, we know that autocorrelation function is E of xt1, xt2. So xt1 is this one with the t equal to t1. xt2 is again this one with the t equal to t2. So therefore, we substitute. Expectation is there. So that expectation is here. Then xt1, a we take out. Here also xt2, a we take out. Now we have cos a cos b form. So we expand it, cos a minus b plus cos a plus b. Right? Cos a minus b, we can see that it is a constant because it is function of omega 0 t1 minus t2. So we take it out. So expectation of a constant is that constant itself. So we have this there. Corresponding to the second term, we can see that it is again a function of phi. Okay, this is constant, so it's a function of phi. So again, it is a g phi. And we want to take the expectation of that. Similar to here, we can see that this expectation again turns out to be 0. So the second term will be 0. Expectation of g phi, that is in the second term, this is 0. So therefore, we have only the first term and we see that it is this one. Now in this example, for this random process, what we have seen is that the mean function is a constant independent of t. And the autocorrelation function is this, which depends only on the difference between t1 and t2, t1 minus t2, not absolute value of t1, t2. For example, if we have t1 minus t2 is the same as say t3 minus t4, then rxx t3 t4 will be the same because it depends only between the difference. It depends only on the difference between these two time arguments, time parameters. Okay. So therefore, if we have t1 plus c and t2 plus c, xt1 plus c, xt2 plus c, for any value of c, we find that because the difference between these two will be always t1 minus t2. So therefore, if you take any two random variables, xt1 plus c and xt2 plus c, the two different time parameters, but c is a constant, then always we get the same autocorrelation function because the difference of the argument parameter will be same, t1 minus t2. Okay, so this is an important thing which we will see later. Okay, so we discuss about that. So this is the example of calculating or computing the main function and the autocorrelation function. Now in this case, we can also find the autocovariance, the third parameter of the random process. Autocovariance is C, we denote it by Cxx. See this to indicate that this is a random process X. Okay. Okay, autocovariance, we use the notation C. Then T1, T2 is equal to autocorrelation function minus mu x T1 into mu x T2. Okay, that is equal to, this is your autocorrelation function, that minus mu x T1 is 0, mu x T2 is also 0, so therefore it is 0. So therefore in this case, the autocovariance function is the same as autocorrelation function. Okay, because the mean functions take the value 0. Okay, now we will define the stationarity property of a random process, because always we talk about stationary random process. Okay, so what is a stationary random process? A stationary process exhibit statistical properties that are invariant to shift in time index. For example, the second order stationarity implies that the statistical properties of the pairs, that is, if we consider xt1, xt2, and we consider xt1 plus c and xt2 plus c, that means we take two random variables which are separated by t1 minus t2 or t2 minus t1, and here again another pair of random variables which are also separated by the same time gap, t2 minus t1, because this is t1 plus c, t2 plus c. So they are separated. I mean, we take another shifted set of, I mean, here we have two random variables at t1 and t2. Here we have two random variables from the same random process, but at the points t1 plus c and the t2 plus c. Okay. So the second order stationarity means if you take any two samples like this from the random process, they will have the same statistical property. Okay, no matter what is the value of C. Similarly, we can talk about nth order stationarity. Nth order stationarity means when you take the joint probability density function of n samples, okay, then we again take another set of n samples, because these are the samples at t1, t2 up to tn. These are the samples at t1 plus c, t2 plus c up to tn plus c. So this is the density, joint density function of these random variables, and the right hand side of equation 14 is the joint PDF of these random variables. x1 prime, which is xt1 plus c, x2 prime, which is xt2 plus c, and so on. Okay, so this is a set of random variables. This is another set of random variables, but we can see that these are parameters t1, t2, tn. These are parameters t1 plus c, t2 plus c, tn plus c. So this set of random variables and this set of random variables have the same joint probability density function or cumulative distribution function. That is, then we say that this random process is strict sense stationary to order n. Okay, so a random process is said to be strict sense stationary to order 1 when we say first order CDF or PDF are time invariant. Order 2, then we have second order density functions, joint density functions are time invariant. And strict sense stationary to order n when we have the joint nth order joint PDF or CDF are time invariant. Okay, and for a random process to be strict sense stationary, then it should be stationary to all orders, all values of n. That is what a strict sense stationary process. Okay, that is, it should be strict sense stationary to any order n. But we know that that is an impossible thing to realize it or check in the reality. So therefore, we should have a looser way or a lighter way of the stationarity definition. Okay, this is what we have already discussed. That is first order strict sense stationary process. Okay, the density function, probability density function of random variable x and random variable x xt. This is the probability density function of the random variable xt, and this is the probability density function of random variable f t plus c. Okay, so so if they are the same, then we know that, because if you put c, this should be true for any c, any c. So for c equal to minus t, we have this is equal to this, t minus c plus c. So it is fxx. That means it is independent of t. Okay, that means the first order probability density function is independent of t means naturally the first order, mean function, because mean function is defined in terms of the first order density function. First order density function is now independent of t. So therefore the mean will be independent of t. Okay, mean will be a constant. It is no more a function of t. because the first order density function is not dependent on t. So the first order strictest and stationary process gives you the main function a constant. Now consider the second order strictest and stationary process. Here we have the density function of xt1, xt2, the joint density function of xt1, xt2, and on the right hand side we have the joint density function of xt1 plus c and xt2 plus c. And this should be, this is the joint density function of these two random variables. They are the same for a second order strictest and stationary process. So, and this should be true for any c. Again, when we put c equal to minus t2, this will become this. Okay, because c is equal to minus t2, so therefore it will be t1 minus t2. So we find that the second order strictest and stationary process gives you a joint probability density function which is independent of the absolute values of t1 and t2 and depends only on the difference between t1 and t2. Okay. So this is the consequence of having a first order stationary process. That is the first order density function is independent of t, and this is the consequences of this results in what? Because we have already the autocorrelation function, we have seen that it is a function of Rxx t1 and t2. So now for a second order strictest and stationary process, this autocorrelation function will become independent of the absolute values of t1 and t2 and depends only on t1 minus t2, because the autocorrelation function is defined in terms of this density function, joint density function. Okay, so now it depends only on t1 minus t2, so therefore the autocorrelation function will depend only on t1 minus t2 and not on the absolute value of t1 and t2. So that will be the consequence of the second order strictest and stationary random process. So that is what is described in this. So the second order density function of a strictest and stationary process depends only on the difference of the time indices. We denote t1 minus t2 by tau. So in that case, the autocorrelation function is given by Rx xs t1 t2 equal to u of xt1 xt2, that is equal to this. Okay. So we find that Rxx t1 equal to Rxx tau, which is Rxx. This is called the conjugate symmetry property. Rxx tau equal to Rxx minus tau conjugate. So the autocorrelation function of a second order strictest and stationary process depends only on the time difference of the time indices. Now we can see that these two properties, that the mean function is a constant and the autocorrelation function depends only on tau. Such a random process is called a Whiteson stationary random process. And Whiteson stationary random process is a consequence that the random process is a first order and second order stationary, strictest and stationary. Because of that we get so therefore a strictest and stationary random process always will be always a Whiteson stationary process. But Whiteson stationary process need not be a strictest and stationary process. Okay. For a process to be strictest and stationary, we know that it should be having the joint PDF or joint CDF stationary to time, which as we defined earlier. So this is the lighter definition or the version of the stationarity of a random process. That is Whiteson stationarity. We did not use the notation WSS. The other one we use the notation strictest and stationarity. So Whiteson stationary means the mean is a constant independent of t and the autocorrelation function depends only on the time difference, t1 minus t2. So as I said, strictest and stationarity always implies Whiteson stationarity, but the reverse implication is not true. Whiteson stationary cannot imply Stichtesen stationary. But there is an exception. That exception is a Gaussian random process. So Gaussian random process, always we talk about Gaussian random process in the communication. For example, we talk about additive wide Gaussian noise, AWGN. Often we talk about the noise at the front end of the receiver as AWGN, additive wide Gaussian. So this Gaussian is actually indicating that the random process that represents a noise at the front end of a receiver is Gaussian random process. Okay. So this Gaussian random process has got the property that Whiteson stationarity also imply Stichtesen stationarity. Why is it so? Because if you look at the joint PDF or CDF of the Gaussian process, Gaussian random process. Of course, now we will discuss the Gaussian random process a little more detail later. So by definition, a Gaussian random process means it samples. You take any number of samples, say xt1, xt2 up to xtn. If you take any number of samples from a Gaussian process, then they will be jointly Gaussian random variables. Okay, that means they have a joint PDF which is Gaussian, a joint Gaussian PDF. And if a joint Gaussian PDF is characterized by the mean function and the autocorrelation function. Okay, so the joint PDF of any number of random variables from a Gaussian, any number of Gaussian random variables, take any n number of Gaussian random variables. You can always define the joint PDF in terms of the mean and the autocorrelation functions. Okay, so in the case of Whiteson stationary process, we know that the mean is a constant and the autocorrelation function depends only on the time difference, depends on tau. So therefore, if you take any number of random variables from a Gaussian process, its joint nth order joint PDF is time invariant or shift invariant because it is completely characterized by the first order and the second order parameters. And the first order and the second order parameters are shift invariant in the case of Whiteson stationary process. And Gaussian random process is completely characterized by the joint PDF of n Gaussian random variables or n samples from a Gaussian process is completely described using this. So here in the slide, actually we are showing Gaussian. Let me go to the next page. Sure. Here we are actually, instead of density function, we are talking about the nth order characteristic function. Okay, let me just mention about the characteristic function. See, a random variable can be, we have mentioned that random variable is either characterized by the density, the CDF or PDF, or we can also characterize it in terms of the transform, phi x. Okay, the transform is actually similar to, in the, we know that for an Fourier transform of a time function ft is equal to, Fourier transform is ft e raised to minus j omega t dt. Right, this is the Fourier transform of a function. Similar to that, we can have Fourier transform of course, no, it's not exactly Fourier transform, but identical, similar to that, of a density function, probability density function can be defined as fxx e raised to minus j omega x dx. Okay, so this is called the characteristic function of the random variable x. Because and it is also, you can, if you look at this expression, this is Fourier transform, because instead of minus sign, here it is plus sign. That's the only difference. Okay, so the density function e raised to j omega x dx, similar to the Fourier transform, except this minus sign, we have plus sign here. So this is the Fourier transform of the probability density function, which is denoted by the characteristic function, which is called characteristic function of random variable x. And if you look at this one, we can see that it is nothing but expectation of e raised to j omega x. because expectation of g omega x, this is a function of the random variable x. So how do you find the expectation? Fundamental theorem of expectation says that the expectation of a function of a random variable can be obtained by using the same expression here, that is the density function of x is used, probability density function, and then corresponding to this one, if this x value takes a real value, so e raised to j omega small x dx. So that is why we say that the characteristic function is the expectation of e raised to j omega x. Similar to this characteristic function, okay, so there is a one-to-one correspondence between the density function and the characteristic function of a random variable. So this is the probability density function of a random variable, and this is the characteristic function of a random variable. If you take the Fourier transform using this, then you get the characteristic function. And if you take inverse Fourier transform, then we get from this one, you can get this one. So a random variable can be completely characterized by either the density function or this one, because there is a one-to-one correspondence. Similar to this characteristic function, you also have a Laplace transform, which is also called the moment generating function, and we have Z transform, which is called the probability generating function. Okay, let me just mention that also in this context. Similar to this characteristic function, we also talk about the Laplace transform, that is the density function. Laplace transform is what? Of a function ft is, Laplace transform is e raised to minus st ft dt. Okay, similar to that, for a density function, we have e raised to plus sx fxx dx. So this is called the moment generating function of this density function. That is, we denote it by mxs. You see that similarity between this and this. Here it is a function of time t. Here it is the probability density function. And instead of minuses, we have pluses. This is called the moment generating function, MGF, of this PDF. Okay. And again, we can see that this is nothing but expectation of e to the power sx. That is, x is a random variable, and expectation of this function of random variable is obtained by using the fundamental theorem of expectation, that is PDF of x, and then e raised to s x, a random variable x taking a small real value small x. So this is called the MGF. So we can write the MGF of a random variable x as expectation of e to the power small sx. Similarly, we have the Z transform of a sequence. Okay, so we know that it is equal to summation x raised to Z raised to n. Let me go. Doesn't go into more details of that and spend more time on that. Here again, we can define it as expectation of for a random okay. So far we were mentioning only probability density function, but if x is discrete, random variable, we know that x can take only discrete values x1, x2, x3, etc. Not continuous like this. So in that case, we know that a random variable is discrete random variable is characterized by probability mass function, which is probability that x is equal to x1 or xi for different values of xi. Okay, so this is the probability corresponding to probability density function of continuous random variable. We have probability mass function for a discrete random variable, which is probability that x taking value, different values, x1, x2, x3, etc. So in that case, we have in the transform domain, what you are having is called the Z transform. That is, we take x to the power n probability x is equal to, or x to the power k probability, Z to the power k probability that x is equal to k. Sum it over all k. So this is the probability mass function of the random variable. And so therefore we can say that this is equal to expectation of Z to the power x. This is the probability generating function of the random variable x, and which is a function of Z. When x is a discrete random variable, we have the probability generating function. So what I wanted to say is that this characteristic function or moment generating function or probability generating function are all the transform domain description of the random variables. Okay. So here I just instead of describing the joint density function in the probability density function, we have the joint characteristic function. Okay, the joint characteristic function is a function of omega 1 to omega n, which and we can see that it is having the main function and the covariance function only. This is the case of a Gaussian random process with the n Gaussian random variables, samples from the Gaussian random process. The joint PDF or the correspondingly the joint characteristic function of that is a function of only mu and first order and the second order statistical parameters. So that is why we say that. You see that to summarize, we say that the Gaussian random process is exceptional in the sense that if it is Whiteson stationary, then it is also Stichterson stationary, establishing the Stichterson stationarity of Gaussian process from its Whiteson stationarity. To summarize, if xt is a Gaussian process, then Whiteson stationary means Stichterson stationary as well. Okay, do you need a break for 5 minutes and then discuss the questions, or should we proceed with the next? Hello?
Ma'am, we have a Q&A session at the end. So I
At the end.
Yeah.
So I can continue now.
Yeah, ma'am.
Okay. So now take an example. Previously we have seen this example, that is the a xt equal to a cos omega 0 t, and which we have seen it is Whiteson stationary. Why? Because in this process we have seen that the main function is a constant independent of t, and the autocorrelation function is again cos omega 0 t1 minus t2, depends only on the difference. So therefore it is a Whiteson stationary. However, this process is not a Stichterson stationary, because if you take the first order density function, you will see that its first order density function itself is time variant. That means if you for different values, it is a function of t. So therefore, even it is not first order stationary, but it is Whiteson stationary. Okay, so that is what it is, not Stichterson stationary process, but it is Whiteson stationary process. Okay, I will skip this second example and then I will go to the next because of the constraint of the time. Now let us look at the systems with the stochastic inputs. Okay, so often we deal with the system. Okay, and at the input we have a random process, and what will be the, and we know the characteristics of the input random process, but we want to characterize the output random process. How do we do that? Okay, so here we consider a deterministic system. Okay, not a stochastic system. A deterministic system transforms each input waveform into an output waveform given by this, by operating only on the time parameter t. Whereas for a stochastic system, it will depend on, it will also function, it will operate on both the time parameter as well as the sample point or the outcome. So our focus is on deterministic system. For the deterministic system, we have a random process xt, and that means the random process xt has got different realizations. We know that each realization is a deterministic function of time t. So corresponding to each realization of the input process, we get a different realization at the output. That is, when the output or the sample point, the random experiment output is xi1, you have one deterministic function, and correspondingly we have a output function. Then for xi2, the second realization as the input, we get a different output. For the next realization of the input, we get a different output. So we get different functions of type t, and collection of this is a new random process yt. So deterministic system can be classified into memoryless system and systems with memory. So we will focus on the systems with memory. There again we have time varying system, time invariant system, and linear system. Okay, of course no, linear system and time invariance and linearity property can be combined, and we have the linear time invariant system. So our focus is on linear time invariant system, LTI system. So for an LTI system, we know that it can be characterized by an impulse response, HT. Okay, and we know that the output of an LTI is convolution of the input and the impulse response. That is integral HT minus tau x tau d tau, or it's a commutative. So therefore, integral h tau xt minus tau d tau. This is for the data. If we consider this is a deterministic signal, this is a deterministic signal, and this is a deterministic signal, and the deterministic system, okay, an LTI system. Okay, now we will skip these slides. Linear system definition and the time invariant system definition I do not have to go through because you are all familiar with that. And the impulse response, you know that for an LTI system, if the Dirac delta function is the input, that is an impulse function is the input, the corresponding response is called the impulse response. That also you know. And also you know that this for an LTI system with arbitrary input, the corresponding output is obtained as the convolution operation of the input and the impulse response. That is what this, which we also already, you also know that. These are all basically input process is input signal is deterministic, system is LTI, and the output is also deterministic. So this theory, this convolution between input and the impulse response is known to you. So now coming to the, as I mentioned, for the when the input is a random signal, then we have corresponding to each realization of the input, we have a deterministic function. So therefore, corresponding to that input, we get a different output, and the collection of all the realizations at the output, we get an output random process. So now we want the mean function, autocorrelation function, and autocovariance function of the output process. Mean function mu yt, we use the notation xt for the input process and yt for the output process. So for the output process, we want to find, we know the mean function of the input and the autocorrelation function of the input. Okay, so mean function and the autocorrelation function of the input are known to us. Obviously, then we have the autocovariance also. We know all these three parameters for the input random process. Now we want to find out the corresponding parameters for the output process. Mu yt, by definition, it is expectation of yt, that is integral e of x tau ht minus tau d tau. Okay, this is the convolution operation between the realizations of the input and the impulse response of the system. And now you can see that of course, no, expectation was outside of the integral. Now we have taken it inside because expectation is a linear operator. So now we can apply that expectation to the random variables here. Here the random variable is only x tau, right? So we apply that expectation to that. So expectation of x tau is mu x tau, then ht minus tau d tau. So therefore you can see that this is convolution operation between mu xt and ht. So the main function of the output process is obtained by convolving the main function of the input and the impulse response of the system. Similarly, we first take the cross correlation, because now we have two random processes. One is the input process xt, the other one is the output process yt. So we take the cross correlation. When we have only one random process, we say autocorrelation and autocovariance. When we have two random processes, we talk about cross correlation and cross covariance. So cross correlation between x and y. See, this is rxy. T1 T2 equal to xt1 yt2. And for yt2, we use the convolution integral between xt2 and the ht. So now you take again expectation inside, and we see that we have expectation of xt1 and xt2 minus alpha. So this is nothing but autocorrelation function of rxx, t1 and t2 minus alpha. So you can see that this is again convolution operation between the autocorrelation function and the impulse response of the system, but the autocorrelation function of the input has two parameters, t1 and t2, and the convolution operation is with respect to this t2 parameter. So therefore you can see that we have written it as rxx t1 t2 convolution ht2. Okay, because the autocorrelation function of the input process has got two parameters, t1 and t2, and the convolution operation is with respect to t2. So therefore we have ht2. So this is the cross correlation rxy t1 t2. Now we can find the autocorrelation function of the output process yt. Now we have the ryy. Okay, autocorrelation function of the output process is by definition expectation of yt1 yt2. Now we substitute for yt1 in terms of the convolution of x and h. Again we take the expectation inside, so we have expectation of xt1 minus beta yt2. So this is nothing but the cross correlation between x and y. So therefore we have rxy. Again you can see that t1 minus beta t2. So now you can look at this one. Here it is cross correlation of x and y, convolution of convolving with the h. This convolution is with respect to the parameter t1. So therefore we have ht1 minus beta rxy t1 minus beta t2 h beta d beta. So we see that this convolution is with respect to parameter t1. Now combining the first two, that is ryy is convolution of, this is your rxy cross correlation, and then cross correlation convolved with ht1, right? So ultimately what is that you are having is, this is your main function of the input process, this is a LTI of the system, and we have the output main function is convolution between this input and main function of the input process and the impulse response, you get mu yt. Similarly, the autocorrelation function of the input, then we have the system impulse response ht2, and the convolution between this and this gives you the cross correlation between x and y, and then convolution of this and ht1 gives you the autocorrelation of the output process. So you see, you got the main function of the output process and the autocorrelation function of the output process from the main function of the input process and the autocorrelation function of the input process and the system impulse response. Okay. And now, if xt is White's and stationary, so our discussion so far was a general random process, any arbitrary random process. Now, if the input random process, if it is White's and stationary, then we know that its mean function is a constant, and so therefore the output, the mean function of the output process is, because mu xt is a constant, you can take it out. Then what you're having is the integral of impulse response only. So which is a constant. So therefore again we find that the output mean function will be a constant independent of t. Similarly, because this is White's and stationary, we know that the autocorrelation function depends only on the difference, time difference. So therefore, the cross correlation function, substituting the previous expression, what you will be getting is this. And again, you can see that it depends only on T1 minus T2. So in this case, we say that xt and yt, the input and output process, are jointly White's and stationary because their cross correlation function Rxy depends only on T1 minus T2, not on absolute values of T1 and T2. So we say xt and yt are jointly White's and stationary. Further, we further apply the formula for the autocorrelation function, the output Ryy, and we see that it is again it depends only on T1 minus T2. So therefore, we find that the autocorrelation function of the output process is autocorrelation function of the input process convolved with the h minus tau convolved with h tau. Okay, so again we find that the output process has an autocorrelation function independent of T1 and T2, depends only on the time difference tau equal to T1 minus T2. So output process is also, when the input random process is White's and stationary, then we find that both input and output processes are jointly White's and stationary, and the output process is also White's and stationary. So summarizing, when xt is White's and stationary process for an LTI system, yt will be White's and stationary. When xt is strict, which we didn't show, xt is strict and stationary, then the output also will be strict and stationary, which we didn't show. Okay, and when xt is equal to Gaussian, then yt will be also Gaussian and stationary, because we will again we have not shown that, but we have mentioned that if it is a Gaussian process, then White's and stationarity means strict and stationarity also. But for a linear system, we know that for a set of Gaussian random variables, a linear system means it will be giving a linear combination of the input. And Gaussian random variables have the property that linear combinations of Gaussian random variables will be again Gaussian. So therefore, we have the Gaussian process at the output. Okay, like Gaussian process, there is another important random process which you often talk about in the communication, that is the white noise process. Okay, so the white noise process and Gaussian random process, Gaussian noise are entirely different concepts. But in the context of additive white Gaussian noise, we talk about a random process which is both white and Gaussian. Okay, so these two concepts are different. Gaussian noise means it is a Gaussian random process. White noise means it is also a white process. What is a white noise process? Okay, that is a different concept altogether. So a white noise process means a random process is said to be white noise if this property satisfies. What is the property? The property is that its autocorrelation function RW. So we use the notation here WT for the white noise. So this is a random process which has the property that its autocorrelation function RWW is QT1 delta T1 minus T2. This delta is a Dirac delta function which we know that it takes value 0 unless T1 equal to T2. It has non-zero value only for T1 equal to T2. Right? So this is an impulse function which has got a strength equal to QT1. Because this is 0 for all values of T1 and T2. I mean, it's non-zero only for T1 equal to T2. So it's an impulse function. So white noise is a random process which has got the autocorrelation function and impulse function. Further, it is White's and stationary means it should be independent of this T1. That means its mean should be a constant. So therefore, this is the definition of a white and stationary white noise. So it is an impulse located at tau, tau equal to 0, okay, with the strength constant Q. That is the definition of a white noise process, random process. Okay. So if this white noise is also a Gaussian process, we already mentioned that a Gaussian random process means it's a samples, any number of samples taken will be a jointly Gaussian set of random variables. So that is a Gaussian process. So if white noise has this property as well as the properties of a Gaussian process, then we say that the white Gaussian noise. Okay, so the white noise. One second. No, one important property with the Gaussian random variables is that if the Gaussian random variables are uncorrelated, then they are also independent random variables. Again, I didn't mention about the independence of random variables, but again, we don't, because of the constraints of the time. I assume that you are all familiar with the random variable concept or the theory of the random variables. So Gaussian random variables which are uncorrelated are also independent. So therefore, we know that the Gaussian process, whose samples are all Gaussian random variables. And now, because the autocorrelation function is 0 if T1 not equal to T2, right? Because of the impulse nature. For T1 not equal to T2, we know that the correlations are 0, and that means the process is uncorrelated. So white Gaussian process means its autocorrelation function is the impulse function. So therefore, they are uncorrelated Gaussian random variables, and therefore they are independent Gaussian random variables. Okay. Now coming to the LTI system with white noise as the input, what will happen is that we know that its main function is a constant. Okay, and output random process has the main function convolution between the mean and the LTI. So obviously we will see that the mean, even though it is mu a constant, but mu convolved with the HT. So HT, H tau, D tau. So you can take mu t minus tau, H tau, D tau, but mu is a constant, so you take it out. So you have mu integral H tau, D tau. So therefore we can see that it is constant. Let me go to the next slide. So the output process, that is, we have input, we have an LTI system HT, the input is white noise, and the output is, we denote it by MT. So the mean function of the output process is given by convolution between the main function. This is the main function of the input, that is mu WT is nothing but mu W itself. It's a constant, okay, because it is, okay, so you find that this is a constant, in fact, that's fine. So mean function of the output is a constant, but the autocorrelation function of the output, Rn and tau, is autocorrelation function of the input is impulse function, convolution with H conjugate minus tau, convolution with H tau, which means we have this. That is, this is convolution between H conjugate minus tau and H tau, that is rho tau, which is obviously it is not an impulse function. So because it is not an impulse function, we can say that the output is no more a white process, because white noise means its autocorrelation function should be an impulse function, but its autocorrelation function is given by Q rho tau. Rho tau is nothing but these two, because this one. So the output of a white noise processed through an LTI system is a colored noise because it is no more white, as its autocorrelation function is not a Dirac delta function. It's a different function, so it is colored. At this point, I have mentioned that white noise need not be Gaussian. That is, whiteness and the Gaussian are two different concepts, as I have already discussed and we have seen. Now, what all we have discussed about the continuous time random process can be applied for the discrete time stochastic process. Okay, discrete time means we can consider it as a sequence of random variables, or we can also consider as the samples of the given continuous time random process. So, a discrete time stochastic process we denote it by xn, that is collection of. Here we have, instead of writing xt with the t in the extra set of random variables where this t is a continuous parameter, now we have xn where n, now this is n is discrete. Okay, so we define it for discrete values of n only, whereas here we have a continuous time parameter, this is discrete time parameter. Okay, that is a difference. So whatever we have explained about the mean function or the autocorrelation function or the autocovariance function, we can apply to this discrete sequence as well. And similarly, the Whiteson stationarity property, that is the mean is a constant, and the autocorrelation function. Now, the autocorrelation function, because we have k plus, so here we have n tau, nt is the period of sampling. Okay, t is the period of sampling. So we have for n equal to, for different values of n, we get different random variables in the collection of the random variables. Okay, so we can, when you take the autocorrelation function, actually we can have the different, the difference of, if it is Whiteson stationary, we know that it is t1 minus t2. So k plus nt and kt. So the difference is k plus ntt, k plus nt and kt means the difference is n. Okay, so nt. So we use the notation like this. Okay, I will discuss. Okay, I'll go to the power spectrum concept. Okay, in the case of a deterministic signal xt, we define the spectrum as the Fourier transform of the signal xt, right? So this is a frequency omega, x omega equal to integral e raised to xt e raised to minus j omega t dt. Okay, this is the deterministic signal xt, and Fourier transform x omega gives you the Fourier transform of xt is obtained using the basic formula. Then x omega square represents the spectrum. We know that from the Parseval's theorem, energy of the signal is given by finite energy signal case. Energy of the signal is given by integral x square t dt, which is in terms of the spectrum, we can obtain it as 1 by 2 pi integral x omega square d omega. That is by integrating this square of the amplitude of the Fourier transform of the signal over the entire range of frequencies, we get the total energy for a finite energy signal. Or in other words, x omega square delta omega represents the signal energy in the frequency band omega to omega plus delta omega. So this shaded area, this is the spectrum, that is x omega square plotted as a function of the omega frequency, and then the value over, multiplying this x omega square with this width, that is delta omega, gives you the energy contained in this band of frequencies. This is known to you because we are talking about deterministic signal xt and the Fourier transform of that and the square of that. Okay, so this is known to you. Now, suppose xt is a random process, stochastic process. Then again, for each, for the random process xt, we know that it's a collection of sample functions or realization. And each realization is a deterministic function of time t. So therefore, for each corresponding to each realization of xt, we can define this, right? But then what happens? Because each realization, when you go from one realization to another, then it will take a different value. Okay, for each realization, this will take a different value. That is x omega square will take a different value for each of the input realization. So therefore, we can say that this is a random variable which takes different values, real values corresponding to each of the realizations of the process xt. So therefore, we need to define E of x omega square. Okay, that is what is done in the next page. Okay, so for a stochastic process, a direct application generates a sequence of random variables for every omega. Moreover, we know that E of xt square is a power, average power we have seen earlier. So for the case of random process, we derive the spectrum in a different way. So what you do is first you consider the process xt truncated to, instead of considering for the entire t, we truncate it to t between minus capital T and plus capital T. So we define a random process xtt, which is the original random process truncated to the interval from minus t to capital T. Instead of minus infinity to plus infinity, we consider this random process only in the minus t to capital T. And then later we will make this capital T to infinity, so that this truncated process will become the original process itself. Now for this truncated process, consider one realization. Okay, so you can take the Fourier transform of that and you get this one. And then we have the square of that divided by 2t. Same thing on the right hand side. Now this represents the power distribution of the, we know that this is the random, this is the power distribution associated with the one realization. We have considered only one realization of the random process. Okay, based on, and it is truncated to capital this random process, not the original one. So we have a random variable, so we apply the expectation. So we apply the expectation xt omega square by this. So if we can take the expectation, substituting for xt omega in the previous expression, and then taking expectation inside, we have this one. So, and this is E of xt1, xt2, and this is nothing but the autocorrelation of the process. So therefore we have autocorrelation of the process, Rxx t1 t2 e raised to minus j omega t1 minus t2 dt1 dt2. And this, suppose now xt is a Whiteson stationary process. It's a Whiteson stationary process. Then we can replace this Rxx t1 t2 with the Rxx t1 minus t2. So substituting for that, for a Whiteson stationary process. Then we have, this is a double integral in t1 and t2. Now we use the substitution of the variable t1 minus t2 by tau. And then this double integral in t1, t2 can be converted to single integral in tau. So that is what is this. Okay, where tau is equal to t1 minus t2. Now in this, we see that this is the power distribution for the truncated random process, where we had truncated the original random process to minus t to plus t. So now we apply minus t goes to infinity, so that the signal become the original random signal, not the truncated one. The truncated one will become the original one by giving t goes to infinity. So then this will become plus infinity minus infinity, and then this term will vanish. So what do you have? Minus infinity plus infinity, Rxx tau e raised to minus j omega tau d tau. What is that? It is the Fourier transform of the autocorrelation function. So what do you get finally? So what you're finding is that the power spectral density of the Whiteson stationary process, which we denote by Sxx omega, is nothing but the Fourier transform of the autocorrelation function. So this is the autocorrelation function of a Whiteson stationary random process xt, and its power spectral density forms a Fourier transform pair. This is known as the Wiener-Khinchin theorem. So we can get the autocorrelation function from the power spectral density using the inverse Fourier transform. Now you can see that with the tau is equal to 0. What is tau is equal to 0 means what? Rxx tau is xt xt1 xt2. And when tau is equal to 0 means that again when t1 equal to t2, we have Rxx t1 minus t2. Okay, so that is Rxx tau. When t1 equal to t2 equal to t and it is equal to 0, then what does it mean? That is E of xt square, right? Yeah, E of xt square, that means which is the power. So what you are seeing is that when tau is equal to 0, this is integral Sxx omega d omega. That is the power spectral density when you integrate for the entire range of frequency, what you are getting is Rxx0, which is nothing but E of xt square, which is nothing but the power. So the entire power from all the frequencies. That is integrating Sxx omega defined in this way over entire frequency gives you the total power in the random signal. So that's how we can confirm that this is nothing but Sxx omega is the power spectral density, because it is giving you Sxx omega into delta omega is the power contained in the range of band of frequencies of width delta omega. So this is actually we are defining some of the properties of the power spectrum. And for the linear system, with the again we can extend the theory that we have already discussed because of the relationship between the autocorrelation function and the power spectral density of a random process, Whiteson stationary random process we are talking about. For the LTI system, we know that the input autocorrelation function and the output autocorrelation function, what is the relationship? The output autocorrelation function is given by input autocorrelation function convolution of this one, convolution of this. Now for a Fourier, in the Fourier transform, we know that convolution operation in the time domain gives you the multiplication in the frequency domain, right? This is the convolution in the time domain. This is the multiplication on the frequency domain. So therefore, we can apply this one to here. So when you take the Fourier transform of this one, that means Fourier transform of this one, we have the product of the Fourier transform of this, this, and this. And Fourier transform of this is nothing but the power spectral density of the input process. And Fourier transform of impulse response of the LTI system is nothing but the frequency response h omega. So this is h minus omega and this is h omega. The product of the two will be giving you h omega square. And this is the power spectral density. So the Fourier transform, when you apply to this equation 71, what you are getting is the power spectral density of the output process. So you have power spectral density of the output process is given by power spectral density of the input multiplied by h omega square, where h omega, which is the Fourier transform of the impulse response, is the transfer function of the LTI system. Okay. Okay, I think this is enough because no, the rest of the thing is self-explanatory. I will be sharing my slides to you so that you can go through the slides, and you can always contact me through mail. You can get my contact details from the coordinators of this process. So I am closing my discussion and open. We have 10 minutes for the question answer session. Can I stop sharing the screen or?
Okay, ma'am. Okay. Okay, now we have a short discussion session. Participants, please raise your questions and doubts related to the topic presented. Please mention your name before you raise the question. Thank you.
Yes.
Ma'am, this is Nidhi Sharma.
Yes, please.
Ma'am, can you explain in the layman language what is the need of this calculation of this PMF and this all in with reference to 5G communication?
But second, calculation of what?
Ma'am, we are calculating something about for a stochastic signal with reference to a wireless network. So when we are projecting all this as a process, so which parameters we have to take as a time parameter and which we take as a random variable for a particular wireless signal? And what is the need of calculating this autocorrelation between two variables, and where we apply all this to a system?
Okay.
In a real life.
May I know your name? Nidhi Sharma.
Nidhi Sharma.
Okay. Ms. Nidhi, actually, have you seen the, I hope you are familiar with the wireless communication fundamentals?
Yes, ma'am.
Okay. In wireless communication, the most important thing is a channel, right?
Yes.
And in the channel, we know that there are three different types of the channel impairments. That is, we have with the distance, we have the receive power decreases inversely proportional to the distance raised to alpha. Okay, that is a deterministic because if we are given the distance between the transmitting antenna and the receiving antenna, you can always calculate the receive power because we know the relation. I mean, it is inversely depending upon the parameter alpha. You can calculate that is deterministic. But then there are two.
Power is power is inversely proportional
I'm
to
coming to
distance.
your question with an example.
Okay.
So the other two effect are the log normal shadowing and that is medium scale fading and the small scale fading. That is log normal shadowing and the multipath fading. So these are actually random phenomena because log normal shadowing is because of the obstruction of the signal by various buildings or trees and etc. And there are different number of buildings, there are different number of trees and all those things. So we cannot predict exactly or we cannot have measurement exactly. So we always go for a log normal model for the for the medium scale fading, right? What is this log normal? What is this log normal? It is again a probability distribution or probability density function which we are assigning to the channel parameter, channel coefficient. Similarly, for the small scale fading, you have multiple signals for this one transmitted pulse. At the receiver side, you get multiple pulses from reflected by different objects in the path from between the transmitter and receiver. So we know that corresponding to a single pulse at the transmitter side, you get multiple pulses at the receiver side. Each one is corresponding to different path. And each path is subjected to different fading amount and attenuation. So at the receiver side, actually, we have to add them together, and what you will be getting again another random process only, random signal only, or the fading itself is a random thing. So how do you characterize that? See, a random process already right from the beginning I was mentioning, it's a collection of random variables. So if you take the signal samples, received signal at the at the receiving antenna, the samples are now random variables because they were subjected to different amount of fading or attenuation in the channel.
Ma'am, how can we decide in the end that this is the we are coming with lots of outputs at receiver side. So
Yes.
lots of pulses at receiver side. So which
Ah.
one is the correct output? How we will decide this?
That's what this is actually a superposition. So we have a superimposed signal at the we have a superimposed signal at the receiver side. So we have to deal with that superimposed signal only. Okay, so the received signal is random in nature now. So you have to deal with the random signal. For that, we should have the fundamentals of the basic, stochastic process. Otherwise, if you take the I don't know which
by
book you
using
follow for 1 second, Nidhi. I don't know which book you follow for the wireless communication, but if you look at any fundamental book in the wireless communication, you will see that your received signal has got it is a random signal, and you always go for the autocorrelation function of that signal, and the fading and all those things are described in terms of the autocorrelation function only.
Okay, ma'am.
Yeah.
That's still fine. We are calculating the expected value of a signal at receiver side.
But
using this
expected value, again, the expected value is only one statistical parameter. That is the first order. First order, that's a mean function. But you need the second order also. Otherwise, no, otherwise your characterization will not be, even second order, including first order and second order, it is only partial characterization of the process. Okay, so first order alone is very, very simple, and that is always, that's not acceptable many times. We need at least a second order also. And the autocorrelation function and the covariance function are the second order statistical parameters.
Okay, ma'am.
And unless you
What is
don't
the
know, Nidhi Sharma, unless you don't know the autocorrelation function, you cannot have the power spectral density, because they are, as per Wiener-Khinchin theorem, which we have just mentioned, it's a Fourier transform pair. So you should first verify that it is a Whiteson stationary process, and we should verify that it is our real. In reality, actually, we are dealing with the signals which are Whiteson stationary. So we don't check for that. But then we should know the autocorrelation function. For example, if it is a white noise, we know that the autocorrelation function is an inverse function. So its power spectral density is a constant. So that means that the power spectral density, because inverse function has a Fourier transform equal to constant. That means that is why the name white noise, because its power spectral density is a constant independent of omega, and that means all frequency components are there. That comes from the autocorrelation function, which is Dirac delta function for the white noise. Did you get it?
Okay, ma'am.
Okay. You have any further question?
Ma'am, what is the third parameter? One parameter of channel. First is the power. Second
Yeah.
is fading concept, and third one is third parameter we
Third
use for
parameter.
the channel.
Okay, for the channel, actually, now we only talk about the mean autocorrelation function and the power spectral density.
Power spectral density.
Yeah,
mean
power
and
spectral
correlation.
density, if you look at that now for the wireless communication channel model, the small scale fading model and all,
This,
yeah.
ma'am, this HT is taken as a channel.
Repeat.
We are calculating in this mathematical example, we are taking HT parameter, na? That is taken as a channel.
Channel, yes.
Okay. Thank you, ma'am.
Yeah, thank you. Actually, I think you should. I mean, there is a need for giving some more basic topics rather than all research topic in FDP. Yeah, because in FDP.
Actually, ma'am, I am from the computer background. That's why difficulties.
Okay, fine. But even for the ECE background also, the fundamental basics of the wireless communication or the stochastic process fundamentals, no, they are not very strong for the even among the ECE faculty. So it's a really needed in the FDPs to give emphasis for the basic subjects also. Because without an insight into these subjects, no, it's very difficult for us to have a research aptitude or have better insight in the research also.
Definitely, ma'am.
Yeah.
Thank you, ma'am. Thank you very much.
Yeah, thank you. I think the answers to Ms. Nidhi Sharma's questions are useful for the other participants also, because these were very generic, very basic things, basic concepts only. So I don't know whether you have enough time for any further questions, or if there is coordinators, please.
Ma'am, there is a question in chat.
Yeah.
It's like, how is this applicable in a
Yes.
how to estimate power and location of station in case of a wireless sensor network if the station is moved around?
Power or location.
Yeah.
Yeah, if that depends on what kind of model we use for the wireless sensor networks. If suppose you have a large number of sensor nodes, then locating individual sensor node is not practical. So in that case, actually, we will be using a stochastic model for characterizing the locations of the sensor nodes, because we cannot identify individual sensors because of the large number of sensors. There again, we have to make use of a stochastic process as a model for the locations of the sensors. But on the other hand, if the number of sensors are limited, and then we have to use a localization process, localization algorithm to identify the location of each node. So that's why it depends on the scale of your sensor network. Whether it is a small network, then we can have individual locations using the localization technique, algorithms available. Or if it is a larger scale network, then we have to use some stochastic model. I hope he got it. Hello?
Yeah, ma'am. Is there any other question? Shall we wind up the discussion session? Is there any
Hello.
other? Yeah.
Hello.
Yes, please.
Actually, I am having a doubt regarding filling the feedback form. What I opened is it's coming like Dr. M. Sankita. Your answer. Shall I write the review of the person?
No, ma'am. I think somebody has edited it. Some participant has edited it.
So
We'll share a different feedback form.
Okay. Thank you.
We'll share it in the WhatsApp window. Okay.
Okay. Thank you, sir.
In that case, now, because there are no more questions, Mr. Shanu and Ms. Roslyn, can I, yeah, please.
Ma'am, as a token of our gratitude and appreciation, please accept the e-memento. On behalf of College of Engineering, Karunapalli, the coordinator and all participants of the ADAL FTP, I express our sincere gratitude to you, ma'am, for the very informative and interesting talk.
Thank you very much. Thanks again, once again, to the coordinators and also all the participants for your patient hearing. I know that this stochastic process, it's maybe a little difficult to explain in this way, but I tried my level best to make it a better presentation using this whiteboard. I hope you will be you have benefited out of this. At least a little bit, to make have a better understanding of your notion of the stochastic process. Thanks again, and all the best for the very successful sessions in the remaining days. Thank you. Thanks again.
Thank you, ma'am.
Yeah.
Next session starts at 11:15. Please take a short break and join on time. Thank you.